Joe Polchinski, he's already getting his microphone, from KITP, talking about the cosmic string inverse problem.
Okay, thank you. So there's been an awful lot of organizer thanking already at this meeting, but it's tremendously well-deserved, and so let me add my own thanks for a really well-run meeting. So I don't have a lot of time, and so there won't be a lot of references. The references will all be in a review that should appear within a week, maybe less. String theories have a very large number of potential cosmic string candidates: the fundamental strings themselves, D strings, various higher dimensional raft brains, and then electric and magnetic flux tubes in the low energy effective theory. And any of these might exist today as a network of cosmic strings. So I don't want that. Oh well. Okay. So when you think about that list, the questions that come to mind are what are the likelihood of sorry. Yeah. Trying to get rid of. Okay. So when you look at that list, the questions that come to mind are, first of all, what are the prospects for seeing any of these if they're there? And if you see something, what are the prospects for distinguishing different microscopic models of the string? So it's the second question that I'm calling the inverse problem, taking a term that's trendy in LHC physics. How do you go backwards from the observations to the microscopic models? And really, there's an intermediate step, namely going from the observations to a variety of macroscopic properties, and then going from the macroscopic properties to the models. So in LHC language, this is model building, and this is phenomenology. And this will be entirely a talk about phenomenology. Now, actually, my title promises more than I can deliver, especially in the time. So rather than thinking about, well, first of all, what do I mean by macroscopic properties? Sorry. Well, obviously, the string tension, the reconnection probability when two strings collide. What's the probability that they pass through each other or reconnect? And that's really a function of the angle and velocity of collision, but to some approximation, just a number. If one just had two microscopic models, basically gauge theory solitons and weakly coupled fundamental strings, this would be enough to distinguish them, but of course there are many more microscopic models. But additional macroscopic properties include what are the light degrees of freedom of the string? Is it just the oscillations, or are there additional light modes on the string? What kind of long-range interactions are there, gravitational only, or do the strings also have gauge or axionic interactions? Is there one kind of string or many? Are there multi-string junctions? So these are the kind of things that you would hope someday to read off from observations if these things exist if they're seen at all. Now my title, again, promises more than I can deliver in the time available, because I'm not going to talk about all of these. I'm really going to talk about the zeroth order problem, what I call vanilla cosmic strings, meaning intercommutation probability 1, and no extra light degrees of freedom, no long-range interactions besides gravity, only one kind of string, no junctions, the simplest thing you can imagine, and also the thing which has been most well studied. But even for these, there are major uncertainties, and so one has to understand this zeroth order problem very well before imagining going on to more complicated kinds of string. So this is a simulation of a network of vanilla strings. The scale here is about half the Friedman-Robertson-Walker time, so a good fraction of the visible universe. And you see a bunch of long strings crossing the visible universe. These are all infinite, they're closed strings. The endpoints are simply leaving the box, and then a gas of loops. And there are simple arguments which suggest that the Hubble length, the size of this box, is the only relevant scale in the problem. And if that had been true, then simulations would have rapidly determined the properties of this network to good precision, and then one could move on to the next step of matching to signatures. But in fact, that's not what happened, because what the simulation showed is that there seems to be more than one scale in the problem. The strings have a kinked structure that persists down to the shortest scales that can be simulated, and also the loops look rather smaller, you see, than the size of the box, and in fact they seem to form at, well, perhaps at the UV cutoff. The simulation obviously has a finite, step size, and so they seem to form at the UV cutoff. And so this, starting with the first simulations almost 20 years ago, this has really remained an open question, understanding quantitatively the nature of the network. The gross properties on the horizon scale, the total amount of string, the total number of long strings, seem to be pretty much in agreement from simulation to simulation, but the finer scale properties are very much up in the air, and because of limitations on time and volume that one can simulate, one is always basically looking at the limits of the simulation and trying to guess which effects are transient and cutoff dependent and which effects are real. And one example of how poorly this is understood is that the estimates of the sizes the typical size at which these loops form, if you look in the literature, the estimates range over more than 50 orders of magnitude, which basically means it ranges from pretty close to the horizon size down to pretty close to the Planck scale in what is a completely well-posed and classical problem. It's just one's inability to solve the equations. And I've been mentioning simulations. You can write down the equations for an ensemble of strings and start to try to solve them, but they're very complicated and nonlinear, and there's been almost no analytic work at all. The analytic models always end up reducing the problem to a few parameters and losing much of the structure. So I looked at this and said, well, look, these are strings. I'm a string theorist. How hard can this be? And that was 3 years ago, so it was hard. And after going through a lot of sort of ideas that didn't work, we hit on the point of view that, look, the real problem is that there's a big range of scales, and this is what field theory is sort of good for. So the idea is to sort of think of it as a field theory problem, sort of letting the simulations work where on the nonlinear physics taking place at the horizon scale, but then trying to use analytic methods to scale to shorter distances. So this is sort of like a renormalization group, although it's a renormalization group backwards from long distance to short. So it's not really, I think, as precise as the renormalization group, but we believe we've had pretty good success in understanding the problem somewhat quantitatively and understanding why there's more than one scale and what the relevant scales are. And I should say that this has been very much with the aid of recent simulations that managed to go a bit deeper in time, and it's a combination of model and simulation. So I'll review the network evolution, our model, and then how this relates to signatures of vanilla strings, and maybe a little bit of the inverse problem. Okay, here there are seven processes involved. You don't have to read this list. Going to go through them one at a time. At least 5 of these have to happen. 1 of them can't happen, and the other one may or may not need to happen. So let me take you through the list. Okay, the network has to form. So the simplest way a network can form, if you have a spontaneously broken U1 symmetry, there will be stringy solitons. If a U1 symmetry becomes broken during the evolution of the universe, then a network of such strings will really form. And in fact, this is just for the gauge theory solitons, but the nice thing is that there seems to be a dual version of this story for each of the different kinds of microscopic strings. So in particular, what really kicked off the recent wave of interest was Sarangi and Tai pointing out that in brain, anti-brain annihilation, you will make D strings through what is essentially just a dual version of this picture. And so you get a network of strings, some of which are loops that decay rapidly, and some of which are infinite random walks that really seed the later network. The thing that can't happen is that these strings can't decay. There are two generic decays to worry about: breakage or confinement by axions. And it's rather model dependent whether these decays are present and whether they're whether they're rapid enough to matter. And so this is the most model dependent thing in the entire subject. We just have to, hope that they're stable. Okay, the universe expands in flat space-time. A string is just a sum of a right-moving and left-moving wave, classically. And in curved space-time, too, you can represent the motion in terms of these right-moving and left-moving unit tangent vectors, but the equations are more complicated because they interact with each other proportional to the expansion of the universe. When long strings collide with each other and reconnect, which we're assuming happens with probability 1, it makes a total of 4 kinks. And this process is responsible for the kink structure that you see on the long strings. The expansion of the universe gradually straightens these kinks, but in fact they form faster than the expansion of the universe straightens them, and so the amount of kinkedness of the network builds up. And that's really why there is more than one scale in the problem. Okay, the long strings emit gravitational radiation, which ultimately will smooth this kinked structure, and so that introduces a new parameter. So the parameter we had before was just the size of the visible universe, T, but now there's a dimensionless combination, string tension times G mu, that appears everywhere, and the gravitational radiation smooths the string at a scale that's much smaller. This is a small number, as we'll see. So it smooths the string at a scale that's much smaller than the scales we've been talking about. Actually, there's an interesting story here that I don't have time for, that it's actually a power of G mu. When long strings self-intersect, loops are made, and the loops decay by gravitational radiation, and you don't need the equations there for the internet, as Jacques points out. Okay, so when all is said and done, you've got those processes. There's this notion of scaling, which is that the net effect of all of that is that if you look at the string network on a scale, again, of the Robertson-Walker time, the Hubble scale, its statistical properties are time independent, so that's the one scale in the problem. If the only thing that we're operating were expansion of the universe, then the scale of the network would grow more slowly as the scale factor, which is a smaller power of T. But the net effect of all of those processes is to get rid of string, and basically to get rid of string as fast as causality will allow. So the typical interstring separation grows not as T to the 1/2 or T to the 2/3, but as T. And this scaling property seems to hold under broad circumstances as an attractor basically mechanism that erases the initial condition. If you have more string, you get more intercommutations. That makes more kinks. That makes more loops. That makes less string. And you can write down simple feedback equations that capture that and show this scaling property. And so the formation doesn't matter. The decays are supposed to not happen. And so these are the processes that are relevant for the network stretching, intercommutation, and gravitational radiation. And for gravitational radiation, it's really just a rule that you remove loops from the simulation after a little while, and you smooth long strings at very short distances. And so here are those estimates that range over 50 orders of magnitude, that the sizes of the loops are close to the horizon size, the original expectation, that they're at the scale which is set by gravitational radiation, which now turns out to be smaller than people initially thought. And there are even argument's not totally crazy. That in fact there's sort of a breakdown of low energy. They're wrong, but they're not crazy. That there's a breakdown of low energy effective field theory, and it's actually the thickness of the string that determines the size of loops that form. So this is sort of 25 orders of magnitude here, and this one's an outlier, another 25 more, but that's still a very wide range of scales. And the first four all scale with t. They all satisfy scaling, but there is a question whether this parameter enters. So that's the question. Here's our model. And so again, the idea was to focus on a little bit of string. I've picked out one of these things and magnified it. And the idea is to focus on a little bit of string in that long network and just follow it. What is its experience? And so there's about 5 things that can happen to it. It stretches via the Nambu equation in curved space. Another long string could run into this little bit of string, but obviously that becomes less and less likely as we consider smaller and smaller segments. So that's parametrically small. This little bit of string could be incorporated into a large loop and disappear from the long string. But that's controlled by the longer scale physics, the longer scale configuration, and won't change the mean ensemble of short segments. In saying that, I'm sort of making it a somewhat uncontrolled approximation. I told you this was a model, not a really totally controlled thing. I'm sort of ignoring the correlations between the configuration at short distances and the configuration at long distances. And if you do that, then again, incorporation into a larger loop won't affect the short distance scale at shorter distances. This might emit a tiny loop, which would seem to matter. To first approximation, we can assume that such small loops don't exist. They do exist, but again, it turns out, as I'll describe, they're controlled by the longer scale physics, and so they can also be ignored to some approximation. And gravitational radiation is again a short scale thing. This is a range of scales at which we can ignore it. And so in fact, if you consider the experience of this little segment, then there's a reasonable argument which seems to be true that its behavior is dominated by just the stretching, the expansion of the universe. Okay, I'm not going to, you can now solve these Nambu equations by separating the configuration of the segment into its center of mass and a fluctuation. And you find the fluctuation basically just redshifts away as some power of the scale factor. And there's a parameter here, the mean v squared, the mean velocity squared of the string. In flat space-time, the Virio theorem would actually tell you that's a half exactly, meaning that these cosmic strings are moderately relativistic, but because of the expansion of the universe, redshifting reduces this a little bit. So from the simulations, you've got to get this number. It's a little less than a half. And so the rate at which these wiggles, the short distance structure damps in time is set by this one parameter that has to be read off of the simulations. You can then, that's the time dependence, the space dependence you can get by matching onto basically at the horizon scale. Again, letting the simulations do the nonlinear work, which provides one additional parameter. But in particular, at the end of the day, you get a prediction for the 2-point function of the tangent vector to the string that has some exponent in it, some non-trivial exponent that's determined only in terms of this parameter v squared that you get from the simulations. And so one can compare now with simulations, and at long distance here, this is long distance, the flatness here of the 2-point function is just a statement that the string is a random walk. And as you come inside the horizon, then rather quickly the random walk seems to bend over to something that seems to match our predicted slope pretty well in both the radiation and the matter eras. And then at shorter distances still, especially here, you can see that these diverge. But that's not at all surprising because these simulations run for an expansion factor of only around 3. And so there's really only time for this range of scales to have come into equilibrium. There's no way they could get the right answer down here. It'd be nice if they could run for longer, but these simulations are very costly. They can't just kind of run whenever we tell them we don't believe them. But this model is working pretty much as well as it could work, and we're pretty happy with it. I think that if the simulations ran forever, you would really see a power law that extends down to eventually you'd run into scales where you'd have gravitational radiation physics. Okay, so that's the 2 points. So that's the first. This is the first quantitative understanding of the short distance structure on the long strings. They're actually smooth at short distance, but they approach smoothness at a rate that's predictable and not so fast. Given that, you can then ask the rate of loop formation, and the key thing here is just this delta function. This delta function just asks the question, do 2 bits of loop intersect? Are 2 bits of long string at the same point in space-time? And so given the ensemble of long strings, you can then ask what's the probability that it intersects itself. And from the 2-point function we found, the main thing is that there are simple scalings of the various components of these vectors and of the various rows and columns of this determinant. So up to some numerical constants, the rate comes out again in terms of these universal exponents that we've identified. So the rate of loop emission goes as the size of the string to a rather negative power. So a small loop doesn't carry off much string, so it's an extra power of L to ask how much string is being carried off by this process. And what one finds still is that even with the extra power of L, for the relevant values of this exponent chi, this diverges at short distance. That is, the string is kinky enough that you tend to form small loops, not large loops. And that's okay, it tells you why there's more than one scale. You'd like to understand what cuts off that divergence, and we think we do. Took us a little time, but this is, again, so the string is a sum of a right-moving and left-moving function. These are the tangent vectors which lie on the unit sphere. They're unit vectors, and this shows them as a function of the right-moving and left-moving coordinates on the world sheet. So a given point on the world sheet is 1 point on this curve plus 1 point on this curve. And although the string is relatively smooth at short distance, these tangent vectors are highly fractal. Anyway, in some sense, as you increase in time, you move along sort of from here to here to here to here to here. And this loop production takes place only in the region of world sheet, where what we've done here is we've separated these tangent vectors into kind of a classical long distance piece and this random short distance piece. And loop production only occurs near the regions where the long distance pieces of the right and left moving tangent vectors intersect. And that provides a cutoff which enables us again to predict the loop production function, which again we say peaks at short distances. And here are recent simulations that actually, these are the best simulations because they've used a trick to run for a very long time, and it's a trick that it seems to work. And these are the sort of the predictions for the slope of this function, which really, again, are no free parameters. And it seems to work. It seems like we have a quantitative understanding of the loop production. Now, actually, there are two, and as the authors point out, there are really 2 identifiable peaks here. The light lines are successive time simulations. The bold line is their final simulation, the longest time they can reach. And there are identifiably 2 peaks, one of which is very close to the horizon size, and one of which is at their UV cutoff. And they believe that the small peak is a transient. We think it's real because we basically predicted it and calculated this property. So this peak is real. This peak at large scales we can't really. This is up in the nonlinear region that we can't talk about. So it seems that one of the reasons that there's been confusion for so long is that there really are 2 peaks in the distribution, and these are the first groups that have been able to run long enough to separate them, and of course in the real universe this separation is much greater. Now you'll notice that it appears here that about 90% of the string goes into the small loops, the loops at the gravitational radiation scale, and only about 10% into the large loops. That's important, and only the simulations can determine those fractions. But that seems, it's not yet a consensus, but here's the scorecard in terms of those initial predictions. Two of them are right. One of them gets a 90% and one of them gets a 10%. But these are the more observable ones. The existence of these large loops is very interesting. So gravitational signatures, these are vanilla. They interact only gravitationally. I'm going to go a little fast because of time. The main thing is that, again, since the interactions are gravitational, the coupling to the metric, Newton's constant times the string tension, is the relevant parameter, and in brane inflation models, this is the interesting range. These can't be dark matter. There aren't enough of them. The perturbations of the CMB come primarily from long strings, which are well understood and have been for a while, and they give the firmest current bound that G mu is less than 2 times 10 to the minus 7. This might improve by 1 or 2 orders of magnitude over a fairly long term. Lensing is primarily from long strings, and the current bound implies a 1 second of arc lens angle. But further surveys in the optical and the radio, again, might get down another 1 or 2 orders of magnitude. I think the greatest reach is in gravitational radiation, which comes primarily from loops, which is why it's so important to understand the loops. And there are two distinctions to make between large loops and small. And in fact, again, both of these seem to exist in the network, and also between low harmonics which get most of the low harmonics of the loop, which emit most of the radiation, and which is seen as a stochastic superposition of many loops, and the high frequency, which is of course these famous cusps. So anyway, to make a long, both kinds of radiation can be seen at the interferometers like LIGO and LISA, but also through its effect on pulsar timing. If signals from pulsars are moving through a fluctuating space-time, they won't be so precise in their timing. And that actually gives already a pretty good bound. The fractional energy density in gravitational waves can't be more than about 4 times 10 to the minus 8th, which, given the current understanding that I told you of these networks, actually translates into a bound similar to the CMB bounds. This will improve by 1, 2, or even 4 orders of magnitude over the next 5 to 20 years, maybe an order of magnitude every 5 years. An order of magnitude here is 2 orders of magnitude in G mu. So this has potentially a great deal of reach. The cusps, which you've heard, so this is good. The stochastic radiation, because of these large loops, is better than was thought previously, more observable, which is good because the cusp signal is less observable than had been hoped. There are a number of suppressions that had been overlooked. And so here's the final scorecard: the current bound, current pulsar arrays, advanced LIGO, future pulsar arrays, and LISA. This is again large loops, low harmonics, what they can reach. The high harmonics, the cusps. Advanced LIGO would have to be very lucky, it turns out, but LISA and future pulsar arrays have a lot of reach. Anyway, my time is up, so I'll just say in terms of measuring the properties, if you see these, well, you might be able to argue from the spectral slope and so on that you have, these are the short-term things, that you have cosmic strings and not something else. To know what even the string tension is, you have to understand the networks very well, exactly how large are the large loops, and exactly how much string goes into the large loops. So even the simplest part of the inverse problem, measuring the string tension, is very dependent on a precise understanding of the networks. Ultimately, if you see something here in any of these, then LIGO will tell you much more about what it is and will help to resolve some of the additional features, additional macroscopic properties that I mentioned. So, okay, So anyway, this has been fun because it was a well-posed problem which was puzzling, and maybe we now understand it, and the simulations were important. It really is a nice combination of analytic and numerical work. Finally, an advertisement. We've been running a lot of string theory programs at the KITP. Well, we're taking a little break to have an LHC program, but mark your calendar for early 2009. All of the organizers are at this meeting. And by the way, one of the pioneers of string theory, who's also the advisor of two of us, will be turning 80 during that period, and so we'll have a short and informal celebration of his birthday. So thank you. Thank you.
Thank you very much. Do we have questions?
You were going pretty quick on it, so what is the influence that a cosmic string has on the galaxy formation? You mentioned real quick.
I'm sorry, what is the information?
The influence that a cosmic string has on galaxy formation.
Okay, so the bounds on the cosmic microwave background, which come from the effect of the long strings, they will make some contribution to galaxy formation, and the large loops will also make some contribution to galaxy formation. And there's been some arguments that especially with these large loops, that this might be observable. This might provide bounds. I would point you at Vilenkin and Olam and Vanchurin for more detail on that. Yeah.
Hi, Joe. You might have said this and it went by me too quickly, but the observational consequences seem to depend crucially on what fraction of the network ends up in loops.
In large loops, not in small loops. Right.
In large loops.
The total amount going into loops is fixed by just energy conservation. And so the total normalization of loop production, and the only thing that's not fixed is the distribution in terms of loop size.
I see.
Yeah.
And then there isn't a good analytical understanding then of what fraction ends up in large loops, or is that something? That's
something which depends on the nonlinear things happening at the horizon scale. Now, maybe it would be, what we're doing doesn't address that problem. You could try to make models, but ultimately I think this is really a job for the simulations. I think this is what they're good at. They're good at problems that have one dominant scale. It may be that and indeed it may be that they need some kind of analytic input about their short distance structure, but yeah, that's why. Yeah.
Thanks.
Have any other? This question here.
Did you ever try to think about, is it working? Okay. Did you ever try to think about domain walls, and in particular light domain walls? I mean, strings are very generic. Domain walls sometimes are generic and also usually very dangerous. But if they are very light, then they will be harmless and sometimes maybe even interesting, because they can possibly explain some correlations between low multiples. So it will be interesting to check whether in string theory you can get any.
Yeah, I have nothing to say about domain walls. They often are related to axions, and so if Ed or Peter, I don't know if Peter Svrchek is here, but people who work on axions in string theory might have more to say about that. I have not thought much about domain walls.
Okay. If you don't have more questions, let's thank the speaker again.